Okay, for this problem, they are asking us to find the frequency in terms of the angle, which is this angle that is right here. I wrote it in the diagram first. Here we're going to have a ball of mass m, and that it's working like a pendulum, and here we have the constant of a spring that it's pushing the ball. So afterwards we're going to determine and remember some of the concepts that are really important to develop this problem. So for the first part, we need to remember for our last part, if we want to find the frequency, that it's F equals, it's important to remember that our omega is going to be equal to 2 pi times the frequency. That is the one that we want to find. Afterwards, the other important formula that we need to find to actually determine the frequency. First, we're going to determine the omega. We're going to select the one about the second derivative of that position plus the angular acceleration squared times x, and this will be equal to 0. So we're going to find a similar equation, but that will be defined for the angle that is right here. So we're going to determine that it's going to be plus square root to the angle plus 0. So this is the one that we first need to find to determine the real frequency. Okay, so for the first part of the problem, we're going to use the symmetry of torques, which will be as the same applied as the Newton's second law, that if we remember is symmetry of forces. I put to MA. So we're going to use now for torques, that's going to be is equal to inertia times the angular acceleration. But why are we using the angular acceleration? This is due to the angle that we're going to use, so it's pretty much different than the normal acceleration, right? Now, another important thing to remember is that our angular acceleration will work as our theta to the 2 points, so to the second derivative of the position. So we're going to use the same as the symmetry of torques would be equal to the inertia times our angular acceleration, right? So now going backwards to the diagram, this movement of the ball is going up, so we're going to have our movement here, and afterwards it will suffer of an acceleration into its to the contrary part of the movement, so it's going to move towards the other side. And now, to do the symmetry of forces, it's important for us to know which kind of forces are acting over our system. So if we have here another marker, yes, we know that there is a force that it's applied by the spring. So what we're going to do is to determine to which side is going to be applied the spring. So our spring is going to act towards this side, so this is going to be our constant times x, and then we're going to have that here is a tension that it's working over our system. Afterwards, we can observe here that also the mass is affecting our whole system, which is mass times gravity, that it's the complete weight. But now when we're going to do the symmetry of forces, it's important to determine which forces are going to work for our problem and which are not going to work, right? So here, we're going to use the point P that actually the only force that is not going to affect our system and we're not going to take into account is the tension that it's right here. Why is this? Because our tension is passing through our action line in the point P. So as it is parallel to it, is not going to move or affect our system at all. Okay, so for the next part, as we know which forces are actually affecting our complete system, we're going to determine how are we going to determine the torques. That, if we remember, it's torque, it's equal to, in vectors, to the distance times the force applied, right? But what is also this? We're going to use it as the distance, perpendicular distance from the action line of the force to the point P where it's going to make the work, times the force that it's going to be applied. So as we know that the only forces that are going to work for our system are the weight and the constant, the spring constant, now we can develop our symmetry of forces. So for the force when we are applying the weight, we're going to determine that the torque of our weight will be equal to the force, that is the weight, that it's equal to the mass times the gravity, times the perpendicular distance applied from the force to the point P here. But let me write the complete system so you can understand. Here we're going to have our action line of our weight, and now we are finding our perpendicular system. We need to remember that this is a perpendicular line. So the distance, the perpendicular distance that we're going to find here to work out, it's going to be determined that this, as you can see, it's perpendicular from the mass to the point P that is located right here. Let me write it again. And we're going to multiply our system times, as we don't actually know a certain value or a certain variable for this part in blue, we're going to take it with our sine and cosine equation, as we have this. Remember? Okay. So we'd like to determine, and this is L, this part, this is L. So we would like to determine which is actually the value of this part. And as we know, if we're acting this, the distance is going to be multiplied by the opposite over the hypotenuse, that it will be equal to the sine value. So here we're going to multiply our weight to take the torque, and the perpendicular distance from this to the point P, it's going to be L times sine of our angle, right? And now we're going to determine the torque for our spring constant. And for our spring, we're going to know that our force is K, constant of the spring, times X, and the perpendicular distance from the spring to the point P. And now we know this is the action line of our spring. So the perpendicular system for this is going to be right here until this point. And as we know here, the H is going to work as the distance, because it's the same distance that is from here to here. So to determine this, we're going to multiply it times H. But now we're going to take out the X, which can be taken out from our system. That, as we know, I'm going to write it over here because it's a little bit full. So here we're going to have our spring. And for something important for us to remember is that this is making a kind of movement like this. So X is for small angles. It's important to determine two things. First of all, when we have a small angle, then our angle will be similar to the sine of our angle. Second, our x, which is this part, is going to be similar to the distance L, the angle times the distance that is acting over the movement, right? This H line that we wrote. So it's going to be similar to OH. So knowing this part, now we can substitute in our equations where the summatory of torques here is going to be, mass times gravity times L. But as we remember here, sine, it's going to be similar to our angle. So it's going to be times the angle. And this, as the summatory, we're going to add the force of the spring. But as here we have our x, that it's going to be similar to this x, we're going to put, as we have, the constant times the angle times the distance times the perpendicular distance from the point P to the point of force. So this will be, the summatory would be mass times gravity times the distance. Now we're going to take out a similar part in both of our variables. So we're having plus the constant as h times h equals h squared, and everything will be multiplied times our angle, right? Okay, so we have now the first part, and what we're going to get afterwards is the frequency. So for this part, what we're going to do is to remember our last equations that we had, and I forgot something that we talked earlier, that it was equal to the inertia times the angular acceleration, right? So with this we can obtain this function that we were asking. And now let me take out this. So we're going to make first that our angular frequency would be equal to the another really important thing is our angular acceleration working here is going to the other side of the movement. This will be a negative movement, or it will go to the other side, so we are going to add here a minus sign as it's moving to the other side. So we're going to obtain that is equal 1 over the inertia, negative, remember, times the mass times gravity times the distance L plus the constant plus the h squared. And now if we remember this also, for a mass m, an object with mass m, our inertia motion or our inertia statement would be equal to the mass times the distance where the point is applied to the square. So we can have that this will be the angular acceleration equal to 1 over minus m times L squared times m plus gl plus k constant h squared. So now, as we have all of our components here, I forgot to write the angle here. We know now that for this part, as we can find this, here is our angular acceleration, and it's going to be, if we put this, it's going to be angular acceleration equals minus omega squared. So here we're going to have the same thing as we have right here, okay? So that will be the same as our actual omega squared. So we're going to obtain that our omega squared is going to be equal to 1 over minus ml squared plus times m gravity mass plus the constant times the h squared, right? And now we want to find the angular velocity of the movement, because what we want is the frequency, and we need to substitute right here. We can find now, so you can see that if we divide everything with this, we're going to obtain by mass 1L. So we're going to obtain that our omega will be equal to the square root, we're passing this right here, times the it's going to be L, the gravity over the distance that we wrote first, minus our constant at times our h squared over ml squared. Okay, so as we know that, we can pass everything to the other side, so we don't have this kind of stuff, and we do not have the negative signs here. We're going to have, it's the same as we got here, just with the negative sign. So it's also going to be minus, so everything is going to convert to plus. And now we know that our omega is going to be 2 pi times frequency, and we're going to find frequency, so we're going to know that our frequency equals omega over 2 pi, and now we can obtain that our angular frequency is this one, so it's going to be the square root of gravity over L plus our constant times h squared over ml squared. Everything would be divided by 2 pi. And this is our final result for this problem. And I am not really good at drawing Cuckoo, so I'll try my best. Here is a Cuckoo girl, and that's all.